In this lecture segment, we will discuss Sonnet SDH. Now, to discuss about Sonnet, let me tell you what Sonnet is. The full form of Sonnet is synchronous optical, that's SO, and network. This is Sonnet, and the full form of SDH is synchronous digital pair. Now, this is our discussion. Now let's come back to the slides. We will be talking about synchronous transport signal, physical configuration, Sonnet frame. Sonnet was developed by NC, and HTH, this standard, was developed by ITUT. Now, Sonnet basically defines hierarchy of electrical signal and optical signal, which is called STS. Now, we will be discussing about STS. This STS, the full form of STS is synchronous transport signal. Synchronous transport signal. We are talking about how these signals being made, what is the hierarchy, how these different signals multiplex together and create signals, and all those things will be discussed. So multiplexing STS frame we will discuss. We will be discussing about physical configuration. We will be discussing about Sonnet frame. So Sonnet is basically the architecture which is used in wide area network. When we talk about WAN, for example, this is home network 1 and this is home network 2. When there is a link created in between these two home network, this is defined by Sonnet. When we have this multiplex and demultiplex signal, we will be discussing about Sonnet architecture. Now this Sonnet protocol, today's high-end electrical electromagnetic signal, optical fiber signal, is actually standardized by Sonnet. So this standardization came from United Standard, NC standard, and from Europe ITUT standard. Okay, these are the defined standard. Now the NC standard, when we talk about the NC standard, it actually talks about Sonnet, and when we talk about ITUT European standard, it's talk about the hierarchy SDH. So that is the reason we talk about Sonnet SDH. Now our discussion is what Sonnet is and what SDH is. So this we are going to talk about in this particular segment. What are the different signals, what are the different devices, what are the different connections, and how this STM is designed. When we talk about STM, it is basically Sonnet transport module. So this Sonnet transport module is basically we need to know when we talk about Sonnet. Now Sonnet has several standards and Sonnet has several devices. To know this, we need to know the architecture of Sonnet. Let us first talk about signal, devices and connection. So this is the architecture. So what happens? Let's elaborate this architecture in a better way. So let me draw the diagram. For example, these are different terminal devices. So this is T1, this is a terminal device T2, this is another terminal device T3. Now what sonic multiplexer will do, this is called STS multiplexer. This we call it as STS mux. So this will actually multiplex all the three devices and give a higher connectivity, which will pass through different repeaters, and this will go. Now we call this particular device as a region. Now when we talk about Sonnet has first STS multiplexer. So one end it is multiplexer and another end this is demultiplexer. So if this end this is multiplexer, when it reaches the other end this will be STS demultiplexer. Now this is all about the Sonnet structure. So in between there is a, now what happens when the signals coming from source 1, source 2 and source 3, for example source 1 is sending some signal to source 2, source 3 is sending some signal to source 2. Now these two signals need to be multiplexed and this need to go to S2. Now some signals coming from S1 which need to go to S2, which will go to S4 as well, and some signal which is coming from S3 will go to S4 as well. So this signal will be demultiplexed here, those who will go to S2. So for example from S1 to S2, this S1 S2 this signal, and from S1 S4 these two signals are multiplexed when it coming from this channel. This will be demultiplexed, and this S1 to S2 and S3 to S2 will multiplex together. So this is the device which is doing the adding and dropping the different signals. So this is called ADM, adding and dropping multiplexer. The device is called ADM. The device which is there in between to do such kind of operations are basically called ADM. Now we have, for example, T1, T2. This signal is coming to multiplexer. This signal initially will come to multiplexer, then this will come to regenerator. After regenerator, it will come to ADM. So this is STS multiplexer, demultiplexer. This is regenerator. Now again, this will go to regenerator. Now this will finally demultiplex and go to the terminal. So for example, T1 is sending some signal to T2. So T1, all other signals will be multiplexed, coming through regenerator, come to ADM. Now accordingly, this will join or drop the signals according to the path. So there are three things in Sonnet. One is called section, one is called line, one is called path. So end-to-end connectivity defined by path. So each and every section need to be defined, and this total connection from multiplexer to ADM, ADM to multiplexer is coming under the line. Okay, so these are the hierarchy of different signals, and these are the different rates of the signals which is there in Sonnet. So now let's list different devices in Sonnet. We have first called terminal. We have first called terminal. Then we have something called multiplexer, STS multiplexer or demultiplexer. Then we have, maybe just can give a name of STS MD. Then we have something called regenerator, which we have given a symbol of R, and we have ADM, adder and add and drop multiplexer. So These are the different types of devices which is available in SONET. Now, when this SONET works in the network, these are different rates of signals. Now, what happens? What is STS1 and STS3? Is basically this STS1 is one single device. Now, for example, this is one terminal 1, this is terminal 2, this is terminal 3. Now, when these three are multiplexed together, this creates a signal which is called STS3. So this is 3:1 multiplexer. Then you can look back and check that this is thrice of the signal. So one STS or one OC1, if you take this is OC1, this is OC3, this is STS1, this is STS3. Now this is 51.840, this is 51.840. If I multiply into 3, this will come under 155.520. So this is in 3 STS1 multiplexed together and giving you the signal of STS3. That is how this STS multiplexed, this is how the hierarchy and signal rates of. Now for example, if you have 4 STS3, you will get STS12, like that. For example, if you have STS3, these are 4:1 multiplexer. Now what happened? This 155.520, this is one, okay, SONET multiplex, this is a one SONET multiplex device. Now what happens? This single channel is STS1 or OC1. Now such single channel multiplex together. Now this 3 channel multiplex together is giving you a signal which is called STS3 or OC3. Now this is thrice of the signal. Now in that case, when it is carrying 3 times of the signal, it will be having huge data which transferred through this particular technology. And in that particular fashion of multiplexing, you can have so many data can be carried through that particular channel. This is the best part of SONET. Now this is a simple network using SONET equipment. Now this is our architecture. This is terminal, this is STS multiplexer, this is regenerator, then add on drop depending on different line. So for example, line which is coming from T1 to T2 will be passing through this particular path, or else if it is for other path, it will drop the signal. So there are devices which is terminal, SONET multiplexer and demultiplexer, same type of devices. We have regenerator, we have terminal. So depending on the connections, so for in between one device to, these are different types of devices. From one device to another device, this is called section. From one SONET multiplexer to ADM and ADM to demultiplexer, this is called line, and this is called total path which is carrying a signal. For example, OC1 is carrying here OC, or for example OC3 is carrying here, OC3 is carrying here. So this entire path is defined by a SONET network, and there are different equipments. Now we will be talking about the SONET layers. So when we talk about SONET layers, we have path layer, line layer, photonic layer, section layer, and relationship in between them. Now SONET defines 4 layers. Now physical layer is nothing but my photonic layer. Now when we talk about connection, normally there are 2 layers, physical layer, and we have something called data link layer. Now physical layer is nothing but my photonic layer. Photonic layer means what kind of signals it carry. The signals it carry comes under photonic layer, and under data link layer we have path layer, line layer, and section layer. So first, from within two devices we have something called section. Now from multiplying different section we have the line and then path. So this is the hierarchy: section, line, and then path. So if you compare to other models, this is physical and data link. So Sonnet multiplexer works in all the 4 sublayers. This works in 2 sublayers. This works in 3 sublayers, and accordingly this is called device and layer relationship. Now, for example, this is my electrical signal. Now, photonic layer can handle different types of signal. So, electrical signal comes from individual devices, then it passes through. If we have an optical fiber cable, FDDI, it will passes through optical fiber, and finally electrical signal. Wherever we have RJ45 connectors, we have electrical signals rest in the path. When we carry high-end connections, okay, then we have FDDI and it carries the optical fiber cable. Now let's do the calculation. What is the size of Sonnet? How the transmission happens? So in this section we are going to discuss about the different. We will calculate different values. Now let's first go and calculate a very basic signal. Now, so first problem, find the data rate of STS1 signal. So we have earlier discussed that it can send 8,000 frames per second. So STS also can send 8,000 frames per second. So now in STS1, how many? This is a frame. This STS frame. Each frame has 9 bytes. And it now STS1, this, if you look into the architecture, it has 9 by 90 frames. So actually 9 into 90 frames. So we will be having 9 into 90, that is 810. So total, if you look into the data rate, STS1 data rate, the STS1 data rate will be 8,000 frames into 9 into 90, and 1 byte means 8 bit. 1 byte means 8 bit. So this will be total data rate. So if you calculate for STS1, it is coming 51.840 Mbps, and that is, if you look into the signal rate, this is the calculation. Now this is my STS1 frame. A single frame is actually having 90 into 9 byte. So this is the architecture structure of a SONET. A single STS one frame has 9 into 90 byte. So let's look into such architecture, how it is. So this is my byte transmission and this is my frame transmission. So that is how we have calculated that any STS1 frame has 8000 frames per second. Okay, and if we calculate the other component, this is coming around this. So we can calculate, if we calculate STS1 signal, it is coming 51.840, and if you calculate STS3, it will be thrice, and in that, okay, it is STS1, STS OC1, it is same. For STS2 or OC3, it is same. Now this is actually SONET architecture. Now if you look into the SONET, you have two things. One is called section overhead, line overhead, and path overhead. So this SONET frames has 90 octets per row and 9 rows, such 9 rows, and this creates a SONET SPE, and in that particular fashion we can calculate SONET data. That's SONET STS. Now let's go and create this structure. Now what happens? This is my single STS frame. This is my single STS frame, STS1. Now in that we will be having 90 octets. Now this is 90. Now this is 0 to 89, for example, 90 octets, and we have such rows which is called 9 rows. So each and every row defines something. So there are two parts. One is called overhead. So this is my overhead and this is my data. Now in that, the first three, 0, 1 and 2, this first 3 octet is basically my header section. So first, and such 3 rows, 3 into 3, 9, this is coming under section. So this is called section overhead or section header. Now remaining 6 into 3, 18. So this is coming under line overhead. Now this together will create a path overhead, and like that, okay, SONET has two portions. Now if you look into SONET, so 3 into 3, this is for, we call it as section overhead. Now section header, section overhead, this is line header. So 6 into 3, 18. So the remaining one, that is 9 into 87, this is for data. So this is STS1. So if you see the overhead, so 9 into 87 is coming for data, 3 into 3 is coming for section header, and 3 into 6 is coming for line header. So this is the SONET details. Now let's come back and see. So in that, this is called my payload and this is called my section overhead, line overhead and path overhead. So total, this is creating my overhead of the SONET. So now we have discussed. So one actually carrying in a 8000 frames in 1 second. So it will take one frame, it will take 1 by 8000 second. So if you calculate, it is coming 125 microsecond. So 125 microsecond is the transmission for one single frame. So this is for SONET. Now the duration of any frame will be 125 microseconds. Now this is, we have discussed section overhead, line overhead and total path overhead, and this is data, and this is my sonnet overhead, how it actually, what is the, this is actually the structure of any sonnet frame, and such 8000 frames carry. Now this is my alignment. If you look into the alignment, we have different measures for identifying different path, line and section, and this is my data encapsulation. Now this is my line overhead, this is my path overhead, and this basically coming under different overhead of different bytes. Now this is coming under, okay. Now let's create one more, let's take one more example for calculation. So now in SPE we have two headers, line header and section header. Now question is, what are the different values of H1 and H2 if the SPE given some specific value. For example, given a value 650. Now this is actually represented, this value, in hexadecimal format. Now 650 is need to be converted into hexadecimal. If we convert into hexadecimal, this is coming 0 to 8 and 8. If we write like this, now this is split into two parts. So first one is called header 1, second one is called header 2. So H1 is nothing but written as 0 into 02, and H2 will be written as 0 into 8. Now in a reverse way, if H1 and H2 is given, then we can actually identify or calculate the sonnet header and the value of the sonnet header subsequently. So that's the problem. Now we can also calculate if we have one for in a 90 column, one for line overhead, 3 for other overheads, then what is this user data? So this is the user data, and remaining data will be my, for 8000 frame, 9, 1 into 86 into 8, this will coming under data. So if you calculate data separately, if you calculate header separately, this will be my value. So these are the different header format, and this we have already calculated. So what are the values of H1 and H2 if the values start from 650? Now sonnet multiplexing, when we talk about sonnet multiplexing, okay, in sonnet all clocks in the network are locked to a master clock. Now when we have such issues, let's see how the multiplexing takes place. We already discussed the multiplexing. Now lower rate can be synchronously time division multiplex into higher rate, like ST1 can create ST3. So we have already discussed. For example, this is my STS1. So STS1, STS1. So such 3 frames can multiplex together and create a STS3. Now if such 4 frames, so this is 3:1 multiplexer, if we have such 4 frames, all are STS3, this will give me STS12. So this is 4:1 multiplexer. So this is, if you look into such architecture, this is totally 12:1. So one STS12 actually carry 3 into 4 STS1 signal, and this is my multiplexing in sonnet. So let's understand the concept of byte interleaving. In solid TTN's multiplexing, we have the concept of byte interleaving. So what is byte interleaving? So basically byte interleaving means, if you look into the architecture, this is called byte interleaving. So this is how, this is coming from STS1, this is coming from STS2, this is coming from STS3, sorry, STS1 terminal 1, STS1 terminal 2, STS1 terminal 3, and they will be taking the position and creating this total, STS frame. Now in multiplexing, in such concept, okay, when the bytes combine together, this is called byte interleaving. So this is the architecture. In combining different sections, we can calculate the byte interleaving in such a way. So now this is my, after calculating from different, this is optical fiber signal CS3 or OC3. This is a signal when we create after byte interleaving, when we have created this signal. So this is the architecture of a bigger signal of STS3. So this is the architecture. Now we can actually create a ATM signal in Sonnet. We can create a MPLS and a high-end WLS standard signals. So now let's understand how this ADM works. For example, from STS3, okay, from this line, this is from L1 to L2. So like this is line 1, this is line 2 in a path. So some signals will go for pass through ADM because this need to go to this particular line 1 to line 2. So corresponding signals will pass, and the one which is not for this, which should not go from line 1 to line 2, will be dropped. So new signals will be added and the old signals will be dropped. In that particular manner, this is working. So Sonnet equipments, we can have different topologies, linear, ring and mesh network. So let's understand the Sonnet network. Sonnet network has 3 types: linear network, ring network and mesh network. So linear can be point to point, multi-point. Ring network is UPSR, VLSR, and mesh can have 2 types: partial mesh and fully mesh. This is a point to point. This is a multi-point Sonnet network, and this is APS for when we talk about ring network. This can create an architecture of a ring. So it's a unidirectional path, this is a bidirectional path, and this is a combination ring which can actually lead to a mesh network. So this is a mesh network. So next we will be talking about virtual terminals or tributaries, which can be a potential payload. So this is how it is creating a virtual system. Now coming back to the briefing of the entire syllabus, let's in this particular section, what we have discussed, how Sonnet is used. Sonnet is basically used in ATM or high-end standard. Frame relay we have not so far used. So Sonnet Sonnet is having some hierarchy to create a connection in between different networks and network standards. And in Sonnet system, we have section, line and path, and we have devices like in hierarchy. We have section, line and path in a data link layer, and we have different wallets, and this has different devices like terminal, multiplexer, regenerator, ADM and multiplexer or demultiplexer. We have different layers. section layer, line layer, path layer, and physical layer, photonic layer. So this is SONET coming under SONET layer. This is coming under device layer relationship. This also required encapsulation. For example, optical signal comes from the basic layer. Now this photonic layer will combine together and give this section, then line, and then path. So this is this is basically inducers. In terminal we have always a electronic data, and in photonics we have optical signal or we have electrical signal. So there is a conversion required. So this is the size of STS 1 frame or STS n frame. This is the overhead, and this is the three overheads: section overhead, line overhead, and path overhead. And this is the different pointers, and we have virtual tributaries, and then we have STS payloads, which we have calculated, STS n. Then we have discussed STS multiplexing. Then finally this is how a ATM signal create ATM. In ATM, how this STS plays a role. Now once we discuss ATM, we will discuss in details. Thank you.